Okay, so let's write the VHDL code for this top label module. So this top label module is our UART module. And this module will have one transmitter section and one receiver section. So we have developed a UART transmitter and one UART receiver. And now if you place these two different modules into one single top module, then this will be your generic UART module, right? So that is going to be very simple for you, because you will have one transmitter module and their ports, and also one receiver module and their ports into one single chip. So that one chip can work as a receiver module and as a transmitter module. So that will be your generic UART chip, and that is very simple. But in this project, we are doing it little differently. So what we will do, we will receive some data at the receiving port of this top level module or this UART module. And then once we receive that data, we will echo it back through the transmitter module. Okay. So that is our project. Means we will receive the data from the receiver module and then we will transmit it back through the transmitter module. Okay. So let's see how we will do this. So as usual, I'm going to write this in Notepad++ first. So create a new file, click on this button. Now first we will save this file. So click on File and Save As. Now go to the UART project folder. Now select the source folder because this is our design file. So that will be VHDL, means Basic Hardware Description Language. Select this. Now we will give it some name. For example, this module name is UART module, right? Now click on Save. Now what I will do, that I will go to this UART receiver module and I will copy its library declaration and entity declaration so that I don't need to write these two things here. So this is our library declaration and this is entity declaration. So first let's change the entity name. For example, this is UART underscore module this time, right? Now copy this. Okay, so this is and entity. We will use this UART module here. Now write the architecture body first. So architecture behave of this UART module is now begin and in the last and behave, right? So this is our architecture body. Now in this entity module, we have this generic section, and because this is our top level module, so we will define all the basic generics and we will also give their values here as well, because this is our top level module and there is nothing higher than this module for this project, right? So suppose my first generic is data width and that is integer type, and I'm saying that the data width is 8-bit. Next is system clock frequency, that is again integer type, and I'm going to use 50 megahertz of clock frequency. So write it 50 megahertz. And we will also use baud rate. So this is integer type and the baud rate will be 115200. Okay, so I think these three generics are enough at the moment. If we need more, then we will define them later. Okay, now coming to this port section. So we will need this clock and reset as an input port. So let's leave them. Okay, and now let's define the other input output ports, right? So what this module will do, that it will receive the data bits one by one on the receiving port. So we will have one input. Let's give it some name. Suppose this input is RS232 receive pin. So let's say RX pin. Okay, so this is our input and a steady logic type. And once we receive it, we will send it back through the transmitter module, right? So we will have one output pin. So let's copy this and let's paste it here. So this will be our transmitter pin and the direction will be out because this is output type. Let's remove the semicolon because we are not needing any other input output ports here. Okay, because everything else will be handled by internal signal. So there is no port for parallel data because we will process it internally. Also, we will handle the other important ports. For example, start signal, ready signal, interrupt request and interrupt request clear. So let's see how we will do that. So for this top level module, we are going to use UART transmitter and UART receiver module, right? So first we will declare these two modules as a component in this module, right? So what I will do that I will go to this UART transmitter module. Okay, so this is Testbench. So I will go to this UART transmitter module, and what I will do that I will copy this entity section and then I will paste it into our top level module as a component. Okay, so this is our UART transmitter module. And now we will change this entity keyword with component keyword, because now this is a component, right? And we will replace this keyword as well. So this is and component. Same thing we will do for UART receiver module. So we will copy this entity part from here and then we will paste it into the top level module, and we will replace this entity keyword with the component keyword. Okay, so this is and component. So now we have these two modules as a component here. So what I will do that I will copy this part, because I'm also going to instantiate these two modules in our program. So I have pasted it in the architecture section. Okay. And now we will do the mapping of these two modules, right? Okay. So first we will do it for transmitter module. Okay. So let's give it some name first. Suppose this is our UART underscore TX module. Okay, and this is a component. Now remove this is keyword because we do not need this. Now generic map. Okay, so let's map the generics. So we have these three generics here in this program. So let's see this TX underscore data width is our TX underscore data width. Oh, sorry, because the generics is data width for this module. So this TX data width will be mapped to this data width here. Next is system clock frequency. So let's see what it is. So this is system clock frequency. Let's paste it as well. So this TX underscore system clock frequency will be mapped to this system clock frequency. Now this TX underscore baud rate. So let's copy this and paste it here. So this is our generic mapping. Let's add the comma here because we have missed it, and let's remove the semicolon from here. Now this is the time for port mapping. So we have these two standard ports, that is clock and reset. So clock will be connected to clock and reset will be connected to reset, right? Now TX start. So let's say we are having one internal signal, that is TX start, and I'm connecting this with this internal signal. Okay. And after some time, we will also declare it. So I'm just marking it so that I remember that we need to declare this TX underscore start as a signal later. Okay, so we will declare it later. Now we have this TX underscore D in. So this is parallel data that is received at the receiver module, right? So let's leave it blank at the moment, and we will do it after some time when we know that what data is receiving. Okay. Now next is TX underscore D out. So this is our output pin. So this will be connected with our output port of this module. And the output port is this RS232 underscore TX pin. So this will be connected to this pin. And this TX underscore ready. So let's create another signal, that is TX underscore ready. And I'm saying that this TX ready is connected to this TX ready. Okay. Now we will declare it as well little later. So that's complete our UART transmitter module, except this D input. We will declare it little later, or we can map it little later. Okay, so let's use the comma here because that will give the syntax here. And now let's remove this AND component part because we do not need this. And now let's map the UART receiver module. So first let's give it some name. Suppose this is UART underscore RX module. Okay. And this is a component of UART RX. Now give the generic map. So let's give it. So we have this data width. So I will copy this and let's map this data width with the data width. And now we will use this system clock frequency for this system clock frequency. And we will use this baud rate as an baud rate for the receiver as well. Okay. So that's complete our generic mapping. And now let's remove this semicolon from here and we will start port mapping. So let's create the port mapping for this receiver module as well. So first I will copy these two statements from here because these are our standard ports, and clock will be mapped to clock and reset will be mapped to reset. And now we have 4 more signals to map. Okay, so let's see how to map them. Okay, so this D in, that is our receiving port of this module. So what I will do, that I will copy that RS232 RX pin because that is our input port. So that will be mapped to this D in. Okay. Now we have this RX IRQ clear. So let's say that we have an internal signal that is RX underscore IRQ clear. Let's say we have another signal that is RX underscore IRQ. So let's map that with the same signal name. And we have this D out, and that is a parallel data. So whatever data that will received at this point, and because this is a 1-bit data, so we will get all the bits one by one, and then this module will convert that data or these individual bits and it will convert it into a parallel data, right? That this RX module will going to do. Okay. So let's say we receive some data and give it some name. So this is suppose receive data. So that is our internal signal where we will store our 8-bit captured data at the receiver port or at the receiver module. Okay. Now let's remove this comma because that is our last port of this module and we are going to declare this later as well. So let's mark it as declare it, and this is vector type. Okay. In this project now, because we are sending the same data, whatever the data we are receiving at this port means at the receiver module, we are sending the same data back through the transmitter module. So this data RX underscore data that we have received at this receiver module, that will be transmitted back through this transmitter module. So this data will be act as an input data for this transmitter module, right? And again, this is a vector data type. So what I will do, that I will map this TX underscore D in with the RX underscore data. Make sense? Now, if you think, then there is a very easy way of writing this module. Can you guess what it is? So let me quickly brief that what we are going to do in this project might be that can help understanding this thing. So what I said, that whatever the data we are getting at the receiver port, we are going to transmit it back through the transmitter module, right? So what you can do, that you can write one single statement that your transmitter data. So what is our transmitter bit or transmitter port? So this is our transmitter port. So this transmitter port will be or will get the value of your receiver port. So whatever data is received here at this pin, immediately that particular bit will be sent back to this transmitter pin. Okay, but we are not doing this because what I want, that I wanted to capture all the 8 bits at the receiver module, and once we captured our data, that is a 8-bit data, then only we are going to transmit it back. Okay, so first we will capture the 8-bit data, and after that we will pass the data to the transmitter module and we will ask transmitter to start transmission. Okay, so we will not follow this easy way here. Okay, so we have done the port mapping of our transmitter module and also for the receiver module. Okay, so we do not need this AND component section here because that will give the syntax error. So I will remove it, but that does not complete our program because we have not still tell our modules that when this transmission start will operate or how this transmitter start pulse will be given to this transmitter module. Same thing for the receiver module as well, because we have not specified that when this RX clear pulse will be given to this module, right? So we need to write some logic to drive these two things. Okay. Now, if you remember from the transmitter module, then this TX underscore start pin was acting as a trigger. Because when one clock pulse is given at this transmission underscore start pin, then only your transmitter start transmitting of data. Okay. And that is one single clock cycle. And that particular clock cycle, it will capture the input data that is received at this point and then start transmitting that particular data, right? So I need to take care that we will only give this transmitter underscore start pulse when all the 8 bits are captured by the receiver module, right? So for this, we will write a process, and this process will be a registered process which is synchronized with the clock signal, right? So first, let's give some name to this process. Suppose the process name is driving TX underscore start signal. Okay, now this is a process. So this is a registered process. So clock and reset will be inside the sensitivity list. Now begin and end process. Okay, so let's write the structure first. So if reset is equals to 1, then do something. Else if at the rising edge of clock, then do something. And if, so what I will do here that I will use a finite state machines to drive this TX underscore start signal. Okay. So what I need only 2 states. That is ideal, means there is no trigger to start the transmission, and the another state will be start transmission. Okay. So first we will declare a data type for this state machine and also one signal for that custom data type. Okay. So let's go to this section between the architecture and begin keyword, and let's declare the data type first. So write type state is ideal, and the another state will be start transmission. So let's give it some name. Let's give it start transmission itself. So start transmission, right? Semicolon. And now we will declare one signal for this data type. So signal current state, so C state, and that is state type. Okay. Now because we are declaring signals, so let's declare other signals as well. So we have this signal TX underscore start. So let's copy this, and this is std underscore logic type. Okay. Now let's make it little clear so that it is easy to read. Now I will copy this signal and I will paste it because we are needing more signals. For example, this TX underscore ready. Okay. So let's define this TX underscore ready. That is again std logic type. We also have this RX underscore data. So let's define this RX underscore data, and this is std logic vector type, and the data width will be this data width -1 down to 0. Okay, so that's good. Okay, let's see if we have anything else. Yeah, so we have these 2 signals as well. So we have this RX IRQ. So let's declare this as well. Okay, so let's copy this and paste it here. And this is our RX underscore IRQ. Okay, we have one more. So let's paste it. And this is our RX IRQ underscore clear, right? Okay, so we have declared all the signals we have used in this program till the time, and also we have declared one data type, and we have also defined one signal for that custom data type. Okay, so we are going to use this custom data type in this state machine. Okay, so let's define that what will happen at the rising edge of clock. So remember what we are doing here. So we are driving this transmitter underscore start signal, right? And this pulse need to be given when we are going to trigger our transmitter module, right? Until that time, we must receive the 8-bit data at the receiver module. Okay. So if you look at this receiver module, we have one signal here that is RX underscore IRQ. And this signal triggered high when all the data is received at the receiver module. So we can use this pin to trigger our transmitter pulse. Okay. But before this, we will write the structure for the state machine. So let's write it. So we have this case that is current state is, now when this is ideal, then it will do something. And now when this is in the start transmission state, then it will do something. And we will have one another case, that is when others. Although this state machine is very simple and it will also going to use only one flip-flop. So the value can be either 0 or 1. So this is a very rare chance that we will come at this when others statement. But still, this is mandate to declare this when others statement, so that for any other condition or any other state, this section of code can trigger. Okay. And you have to declare it despite how complex your system is. So this section is here when others, and it will do something when this case, and in the last we will AND this case statement with the AND case. Okay. Now what will happen when this current state is in ideal condition? Means we are not triggering any pulse to the transmitter module, right? So as I said that we will monitor this RX_IRQ signal, because this will trigger high when all the 8 bits are captured at the receiver module, right? So what I will do that I will monitor this signal. So I will use this if condition. So if this RX_IRQ gets 1, then our transmission should start. Means our transmission_start should drive it. Okay, so this will be 1. Also, we wanted to move to the next state, right? And our next state will be start transmission. So our current state will move to the start transmission, right? Now, and if. So now we are at this start transmission state, right? So first what I will do that I will reset this transmission_start signal. So this will ensure that we will get this pulse for only 1 clock cycle, right? And also once I am here, my current state will also change to the ideal, because I only want 1 pulse at this transmitter_start signal. Okay. So this will ensure that only 1 clock cycle is given. But we have one problem here, that what will happen when this RX_IRQ signal is triggered, but our transmitter module is still busy in transmitting the previous data. Because UART receiver module can receive data at any point of time. And there is a possibility that when we capture all the 8 bits and when this IRQ signal is triggered or asserted, and that time our transmitter module is already transmitting some data. So that can create some problem, right? So we also need to think on that perspective. So how we will solve this problem, that if we look at the transmitter module, so this is our transmitter module, and here we have one output port that is transmitter ready. And if you remember, this TX_ready port is high when there is no data transmission is happening. And when some data transmission is happening, then this port gets low. So that tells that when the transmitter module is busy in transmitting data and when it is an idle state, right? So when this port is high, this means that our transmitter is ready to transmit a new data. Means currently it is in idle state, right? So I can use this TX ready port here in this condition to tell this process block that when you should drive this TX_start pulse. Okay, so when our transmitter is ready, then only we can give a pulse, right? So I will add a condition that RX_IRQ is 1 and TX_ready is also 1, then only it can give a transmitter pulse. Okay, so I think this is good and that can work, that what we are expecting from this. So let's define that what will happen at this when other condition. So what I want that any other condition, I will move to this ideal state. Okay, and also that will be our reset condition as well. So when the reset will be applied, we will be at ideal state. And also I don't want to send any start pulse when the reset signal is given or reset signal is asserted. Okay, so that's good. And now we have only one thing to drive, and that is for the receiver module, and that is RX_IRQ clear. Okay, and for this project, when we are echoing back our received data, we can drive this with this TX_start signal, right? Because when we receive all the 8 bits at the receiver module, then this RX underscore IRQ signal will be triggered. And to clear this interrupt request, we are sending this clear signal, right? And if we think logically, then we have this transmitter underscore start signal, and we have driven this in such a way that it will only trigger when all the 8 data bits are captured, right? So what I can do that I can move this transmitter underscore start pulse to this RX underscore IRQ clear. Okay. So this clear, interrupt request clear, will get the value of TX underscore start, right? And hopefully that solves our requirement. Okay. So I think we have declared all the signals that we have used internally in this module, and we have derived all the important signals as well, right? So I hope that should work fine. So this is the time when we will compile this program in the Model Sim Simulator. And let's see if this program has any syntax error or not. Okay, so let's save this file. Now open the Model Sim Simulator. So Model Sim. Now let's maximize this window and now add our UART module in this project. So right click on add to project and then existing file. Now click on browse. Now go to this UART project folder and click on this source folder. So we can see this UART underscore module file here. So let's select this and click on open. Now click on OK. So this file is listed here. Now right click and then click on compile and compile selected. Okay, so the compilation of UART module.vsd is successful, means there is no syntax error, and that's good. So now this is the time to write a test bench for this module, right? So now this is the time to write a test bench for this module, right? So for this, we will go to the Notepad++ once again. And first we will create a new file and then we will save it and click on Save As. Now this time I will choose the test bench folder because now we are writing a test bench. Now first we will select the file type. So this is VHDL. So we will select basic hardware description language. Now we will give some name to this file, and suppose the file name is UART module Testbench. Okay, now click on save. So what I will do that I will copy this part from here. So let's copy this part from here and let's paste it. Okay. And the first thing that I will do that I will correct the entity name because this is a test bench. So let's update this entity name. Same thing here. So this is a test bench. Now this is the architecture body. So use it, begin, and in the last and architecture. So that's complete our structure. Now because this is a test bench, so we do not need any port listed here, but I will leave these generic section at the moment. Okay, so now let's declare a component. So for that, what I will do that I will copy this entity part from this UART module and I will paste it in the declaration section of this architecture. And now we will replace this entity keyword with the component keyword because this is a component here. And now paste it. And now I will copy this one more time and then I will paste here in this section. And here we will instantiate this component. So this is our unit under test. So that is our name. Now remove this is keyword from the last. Now give the generic map. So let's say our data width is integer and this is 8-bit, or even we can use this data width, or even we do not need this generic map as well. So we can delete it here because this is the only component listed here. So we can change it directly from here. So what I will say that we have this data width and that is integer. So this is 8-bit wide. Our system clock frequency is 50 megahertz and our baud rate will be 115200. Okay. Now let's remove the semicolon and use the comma instead. Okay. And let's remove the semicolon from here as well. Now there is one more thing to note here, that if you are instantiating or if you are initializing your generic values in the top module, like here we did. So here for this UART module, we have defined all these generics and we have also initialized their values as well. For example, data width is 8, system clock frequency is 50 megahertz, baud rate is 115200. So if they are declared in the module itself, which you are going to test, and if you want to do the same values in your test bench, then in that case, you do not need to define this mapping. Okay, so you can completely eliminate this or you can completely delete this from here and that will work fine because you have already defined these values here, right? But if you are writing them or you are mapping them, that is also fine. Because if you wanted to play with this test bench for some other values in the future, then you can do this from here. Okay, so I will leave these values here as it is. And now this is the time of port mapping. So let's write it. Port map. Now clock will be connected to clock. Now reset will be connected to reset. Now this receiver pin of RS-232 will be connected to the same pin and same for the transmitter pin. So this will be connected to the transmitter pin. And now we will delete this AND component section in the last, right? So this is our component instantiation. And now we will declare these 4 signals here in this program. So let's declare them. So this is signal here. So now signal, copy, paste, paste, paste. Now, because these are signals, we do not need to write the direction here. So let's remove them. Okay. And we will add semicolon in the last. Also, we are going to initialize this clock value with 0. Okay. And now first we will drive this clock signal. So I will write the statement that clock will get the value of not of clock after 10 nanoseconds. So this will generate a 50 megahertz of clock frequency, right? Okay. So we have 3 inputs in this component of UART module and we have derived this clock signal. So we have these 2 signals we need to drive. Okay. And for this, I will use a process block. Okay. So first we will give it some name. So the name of this process is suppose test process or test driver. And this is a process. Now I'm not giving anything in the sensitivity list because we are going to use wait statement inside this process. Okay, so let's start this process with the begin keyword. In the last, we will have wait statement and finally end process. Okay, now we will write the code to drive this reset signal and this RS232 RX pin signal. Okay, so as usual, we will initiate our simulation with the reset condition. So initially our reset will be high, and also when this reset is high, I want this pin at the ideal state. Okay, so reset is high and also this pin will be high. And this is high because of RS232 protocol. Because when there is nothing to receive or nothing to transmit, then the state will be high and our start bit is 0. So at the ideal condition, we would be getting logical high, right? So at the reset condition, this is high. Now this reset condition will be applied for initial 100 nanosecond. So we will wait for 100 nanosecond, and after this 100 nanosecond, our reset will be deasserted, right? And then we will also wait for another 100 nanosecond. Now after this 100 nanosecond, we will start receiving some data at the receiver port. Means this pin will get logical low at this point. So this 0 is actually our start bit, right? And now we will wait for 8.7 microseconds because this is our bit period. And after this start bit and waiting for 1 bit period, that is 8.7 microsecond, we will receive our actual byte, and that will be received one by one. Okay, so what I will do that I will copy this statement or these two statements multiple times. Okay, so that will be repeated 8 times because we would be getting 8 bits, right? And suppose instead some hard-coded value, we are getting some data that is stored in some signal or variable. And suppose the data is test byte because this is a byte and we are getting data one by one. So I will say that at the very starting, I will get this test byte 0. So I will copy this and same thing will be repeated 8 times like this. Okay, so why have I started from 0? Because RS232 protocol transmits the least significant bit first or LSB first. Same at the receiver side, it will receive the least significant bit first. So this is our least significant bit. So this is 1, this is 2, this is 3, and it will go up to 7. And in the last, we will receive stop bit. So that will be 1. So I will copy this part from here and now I will replace this 0 with 1. So this will be our stop bit, right? And this will be our start bit. Now for this 8-bit data, I can use a for loop. Okay, so what I will do that I will use a for loop that is for I in 0 to 7 loop because we have 8-bit data. Then I will need these two statements here and in the last AND loop, right? And this data byte 0 will be our I. Okay, so for this 0 repetition, this value will be test byte 0. For the first repetition, this will be test byte 1. For the second repetition, this will be test byte 2. And this will be repeated up to 7. Okay, so we will get total 8 bits starting from 0 and go up to 7, right? So that's complete our test sequence. Now I will save this. Now one thing to do that is driving this test byte, right? And this test byte can be any data. Like it can be integer that is converted into a 8-bit data, but that can be a ASCII character or it can be anything. And because this is our final module, I wanted to test this module on multiple data. So the question is that how you going to test this module multiple times on multiple data. So one thing is that you can repeat these statements multiple times here, and every time you can send a different data to this test byte. Okay, for example, this test byte here, or you can update it here. So you can say that this byte is suppose integer 01, or even because this is a vector type, so even better if you give a hex value. Suppose this is the test byte first And now for the next test sequence, this is here. And for the next test sequence, it is something like 03, or this is 02, like this. So you can test your module like this. But what if you wanted to test this with 255 character of data or even more? So in that case, this is not a good approach, right? So in this session, I'm going to tell you the easy way of doing this. And for this, we are going to use a procedure in this program. So first, I will remove everything from here because we do not need this. Okay. I just need a test sequence that we have written initially, and we also do not need this. So basically from here, our test sequence is started. Okay. So from here, our test sequence is started, right? And this goes up to here, right? So what I wanted to do, that I will pass some data to our procedure, and then procedure will act based on that data and come back. Then it will take another data and run the complete procedure for the test sequence for that new data, and then come back here. Again, it will capture the new data, work on that and come back, right? So that's what I want. So let's write the procedure for this. We will start it here in this process. So first write a keyword, that is procedure. Now we will give it some name. For example, this procedure name is test sequence. Okay. Now we will write the framework first. And what I'm going to do, that I wanted to define a constant here. Suppose the constant is test data, and that is integer type. Okay. Even though we do not need to add semicolon here, because that is only one thing that we are defining. If you are defining multiple things here, then only you need to add semicolon. And for the last statement, you will not add any semicolon because this is a last statement. So I will not add it. And whenever we will call this test sequence, which is a procedure, we have to pass this test data. And this test data will be integer type. Okay. Now we will write begin, and in the last and procedure. Okay. So if you notice that we have a test sequence here that we have already written to send a 1 byte data, right? So what I will do, that I will cut this data from here, or I will copy this and I will paste it here in this begin section. Okay. So what will happen whenever this test sequence procedure is called, this set of statements will trigger or will execute. And what it will do, that it will insert the start bit first, then it will transmit the 8-bit data, and then it will transmit the stop bit. So that is our test sequence. And now because we are using this test byte, so we need to declare it. And this time we will declare it as a variable inside this process. So now this is a variable and this is a test byte, and this will be std_logic_vector. And the range will be 7 down to 0, right? Or even it will be better if we define a generic for this data width. Okay. So what I will do, that I will define a generic here with the same name, data width, and that will be integer type, and its data will be 8. Okay. So I can use this data width now in this program. So this test byte will be our data width -1 down to 0. Okay. And I can use the same thing here, because if we are changing this data width, then this loop data will also change. Okay. Now we have one problem, that this test byte is actually a steady logic vector. So that is good because we are transferring this data one by one on this receiver pin. But the input data that we are passing to this procedure, that is integer type. So this test data is integer, but this test byte is a steady logic vector. So I have to convert this integer data into a steady logic vector data type. Okay. Because remember, VHDL is a strongly typed language. So the assigner and the assignee must follow the same data type and as well as same length, right? So before starting this test sequence, I will change the data type of this test data into the test byte. Okay, so what will be our test byte will be, so this test byte will be, so we will use a function that is to unsigned. So that will convert an integer value into the unsigned. So we will pass our this test data because we wanted to convert this data into the vector type. So this test data will be converted. And now I have to tell that in how many bits this data will be converted. So for this program, this test data will be converted for 8-bit data. Okay. Now I wanted this to be std_logic_vector. Okay, so this is the statement that will convert this test data into the std logic vector, and that data will be passed to this test byte. And this test byte will be used here, and from this data, our receiver will collect all the bits one by one. Okay, so now I will save this. And now the only one thing that is left, because we have defined this procedure, so I can use this to drive our test sequence. So what I need to do that I need to call this procedure here after the reset condition. So what I can say that our test sequence, because this is our procedure name, so call this test sequence, and this test underscore data will be, that is our constant integer. Now you can give any data here, and that will be act as an integer data. For example, you have passed this test sequence 33. So what it will do that it will call this procedure test sequence, and it will pass this 33 to this test data. Now this test data 33, which is integer, that will be converted into the std logic vector, and then this test sequence will start. And the test sequence will be start bit, that is 0. Followed by the 8-bit data, that will be the converted value of this 33, and then followed by the stop bit, that is 1. Okay. Now suppose I want to test this module with more data, then I can do this by simply adding more test sequences. Okay. For example, we can add more test sequences like this. Even though we can add some little pause here, so we can wait for something around 20 microseconds, for example. And then we can pass multiple data. For example, I can test it for 33 value, then 34, then 50, and multiple sequences you can add. Okay, so for now, for example, I just wanted to test this for one value, that is 33. And if you convert it into the hexadecimal, then that will become hex of 21. Okay, so we would be getting 00100001. So we would be getting this data at the receiving module, and the same data will be transmitted back from the transmitter module. Okay. There is one more thing to do here, and that is because we have used the function that is toUnsigned, and that is not defined in this 1164 package, but this is defined in the numeric_std package. So I have to use that package to use that function. So that is use IEEE.numeric_std.all semicolon. Okay. And now I think everything is defined. All the signals are defined. Components are defined. Generic is defined. Then we have the test driver. So this is a process to drive this reset signal and this RS-232 RX pin. We have drive clock. So all the three inputs has been driven, and we have also instantiated the test module, that is UUT. Okay, so everything is good. So I will save this and I will go to this model sim simulator. So first thing that I will add this file into the project. So I will select this add to project and then click on existing file. Now click on browse. So this time that is saved inside this Testbench folder. So I will open it. And the file is UART module_testbench. So select it and click on open. Now click on OK. Now let's compile this program. So select this, right click, compile, then compile selected. Okay, so I can see there is one error at this line number 14, and it is saying expected identifier. So let's go to the line number 14 and let's see how this is complaining. Okay, so there is no port, so delete this section here. Now save it, and let's go to the model sim simulator once again. Now compile selected. Okay, now what it is complaining about? Now it is complaining at line number 52 and 66. Okay, so go to 52. Okay, so the problem is here. So we have used semicolon. Instead, we have to use is. And now everything is good. So let's save this and we will compile our file one more time. So compile selected. And now we come up with one more error. So that is line number 52. So let's see what it is. So target of signal assignment is not a signal. Okay, so the problem is with the assignment operator. Now because this is a test byte and that is a variable, so we do not use this symbol as an assignment operator for a variable. This is the assignment operator for a signal. And in VHDL, a variable assignment operator and a signal assignment operator are different. So this is for signal and this is for variable. Okay. Okay, so now save this file and we will compile our program one more time. So let's right click, compile selected. And you can see that compile of UART module _tv.vsd is successful. So this is good that we do not have any syntax error. So now this is the time to simulate our program. This is the time to simulate our program. So for this, I will select this library tab from here and I will look for the work library so that we can see this program, that is a Testbench for UART module. So here it is. Now I will click on simulate. Okay, so now select the waveform tab from here. And I am really interested in this UUT or unit under test. And you can see that all the signals and generics are listed here. So what I will do that I will select all the signals that I wanted to evaluate and then I will drag them into the waveform window. Okay, so these are the signals I wanted to look for. And now I will drag them into this waveform, right? So let's adjust this window so that we can have a better picture of this waveform window. And this is good. We can see all the signals in one row. And now because we are transmitting 33, that is in integer format. So let's see if we are receiving the right data at the receiver module and then the right data is transmitted through the transmitter or not. Okay, so for this, let's trigger our simulation for 200 microsecond. Let's see if everything is covered or not. Okay, so let's zoom out a little. So I can see that something is happening, but till now I don't know that everything is good or not. So let's test this. Okay. So first I will start from the starting. What is happening in the starting? Okay, let's zoom in a little more. So this is our reset condition. So that is applied for 100 nanosecond. Okay. And after 100 nanosecond, this is 0. Okay. So this is applied till here for 100 nanosecond. And after 100 nanosecond, this is deasserted. So this is 0. Okay. And after another 100 nanosecond means total 200 nanosecond, we have derived our RS-232 receiver pin. So we have passed the start bit here and the start bit is 0. So you can see that at this 200 nanosecond, this RX pin here this RX pin goes to 0. So that is good. And now we will see if we captured the data or not. Okay. So this received data has been captured for 8 pulses for the data and for the 10 pulses including start bit and stop bit. Okay. So this is the first start bit and the data starts capturing from here. So one bit will be captured here, then second bit will be captured, third bit, 4, 5, 6, 7 and 8. So this will be our 8th bit. So first what I will do that I will change the radix to this hexadecimal for the first time, and then we will see as an integer data as well. Okay. So you can see that after 8 pulses has been completed, so from here to here, we would be getting 21. And if you notice that when we are getting this 21 as a received data, we have triggered this RX IRQ, which indicates that all the 8 bits has been received by the receiver. And now this is the time when the received data has to be transmitted back, right? So if we zoom to this particular area when this thing is happening, so let's drag it here. Okay. So you can see that this current state is at ideal till this point, and at the same time our ready signal, that is our transmitter ready, that is also 1. Means this transmitter module is ready to capture a new data and ready for the transmission, right? And this is dependent on the interrupt request signal that is triggered by the receiver module. Okay, so once all the data is collected, this IRQ is triggered. And after one clock cycle, we have triggered this transmitter start. So at this time, it has captured the input data. And if you see, the input data is 21 here at this point. So you can see this RX data, it is 21. So this 21 is captured by the transmitter, and now it will start transmitting out data. Okay. And you can also see that the transmission start is only given for one clock cycle. So this is the one clock cycle, right? Or if you wanted to test the baud rate or even the bit period, then you can also look for that. So you can see that these pulses here are expected to change at every 8.7 microsecond, right? So if I add a marker here and if I test this point and up to this point, so that must be near about 8.7 microsecond. Okay, so this is near about, let's zoom it a little so that we can see, or even a little more. Okay, from this point to this point, that should be near about 8.7 microsecond. So if we adjust this little more, we will see that is near about 8.7 microsecond. Okay, and the first bit or the bit period of the first bit would be half of the bit period for the receiver, right? So if you look for the first bit, so that would be near about 4.35 microsecond. So that should be near about 4.35 microsecond. Okay. Okay, so if you zoom it a little more and if you adjust the window or the slider, then you will get the similar value. Okay, so that will be near about 4.35 microsecond. Okay, so you can see that is 4.35 microsecond near about. So that is good. That is inside our range. So that is good. Now let's compare the received data and the transmitter data. Because we have transmitted our data one by one, and after it's transmitted back, we have not captured the parallel data. So we have to test our data sequentially. So let's give a quick look. So for example, here we have this data that is 0. So that is our start bit. Then we have passed 1, then 4 times 0, and then 1, then 0, 0, then 1. So that is our received data, right? And we have sent the same data back through the transmitter, right? So if you compare this section, this timestamp, so that will be matched to this point. So that is our start bit. So this is our start bit, followed by the next one pulse, followed by the next one pulse, then 4 pulses of zeros, then 4 pulses of zeros, then one high pulse, then one high pulse, then 2 pulses zeros, then 2 pulses zeros, and then one stop bit and then stop bit. Okay, means whatever the data we have received at the receiving port of the receiver module, the same data has been transmitted back, right? But you can notice that this is a laborious work because we have to test our test sequence manually for each data bit, and we can improve this. How? So what we will do, so we will capture that each and every transmitting bit, and once all the 8 bits has been captured, we will convert them into a parallel data. And then we can compare that the received parallel data and the transmitted parallel data are same or not, right? For example, this hex value 21 that we have received, then the same data has to be transmitted. And by doing this, we can compare the actual value in the hex format or integer format. For example, if I convert this into the integer, so if I change the radix to the unsigned, so you can see the data is 33 that we have passed into the test sequence here. So you can see the test sequence 33. And now, for example, I want to test the another test sequence, for example, 34. Then I just need to write these 2 lines. Okay. And now if I simulate our simulator, then let's see that what is the output. Okay. But before this, because we have changed the program, our VHDL program for Testbench, so we need to compile our program first. So what I will do that I will right click here and then compile selected. So this is good. And now I will restart my simulation. So here is the button, restart. Now click on OK. Now because we are transmitting 2 data bytes, so I have to run my simulation for a little more time. For example, this time I'm running my simulation for 400 microseconds. And let's see if we have captured all the data or not. Okay, so let's zoom out. Okay, so we can see that here we are getting the transmitting pulse for the first test data, and here we are getting the another transmitter pulse for the second data. And this is for the transmitting of data, right? So first we will see that what data we have captured. So this is the first data and we have already compared this 33 data. So up to here, we are busy in transmitting the first byte. So if you can look at this radio signal, so this is high. So this is high means there is nothing is transmitting. And when this is low means some data is transmitting, right? Okay. So we are busy in transmitting our first byte up to here. And that was our first data, that is 33. And from here, we are start transmitting the second data, and that is 34, right? So the hexadecimal value of 34 is 22. So let's change the radix of this to hexadecimal so that we can easily visualize it. So the value is 22, means the data is 00100010. And now because the data is transmitting the LSB first, so the sequence will be reversed, right? So the sequence will be 01000100, right? So let's see if we are getting the right data or not. So this data from here to here, that is our start bit, and our actual data will start from here. So that is 0, 1, 0, 0, then 0, 1, 0, 0, and this is start bit, right? So this means that our simulation is getting the right results. But as I said, by using this method, we are testing our data for each bits, right? And that is little time taking process. So what I will do that I will modify our program for this test bench to capture the parallel data which is being transmitted from the transmitter module. Okay, so what I will do, I will create another process for capturing the parallel data. So let's give it some name first. So capturing parallel data at transmitter. Okay, you can give any name you want. So this is the process. Now begin. Now when we are starting our transmission. So we are starting our transmission at the falling edge of our transmitter pin, right? So what I will do that I will wait until falling edge of this RS232 transmitter pin. Okay. Now we will wait for the half of the bit period. So that is our 4.35 microseconds. And now I will use one loop for capturing all the 8 bits. So what I will do that I will use this loop for IN02 data width -1. Let's see if we have defined the same generic or something else. Okay, so there is an underscore in between, so that's good. So 0 in 0 to data width minus 1, that is a loop. Now first we will wait for 8.7 microsecond. So that is our 1 bit period. And now our transmitting byte of I index will capture the current transmitting data. And our current transmitting data is the data that is available at this pin. Okay. And now this is AND loop, because that will capture all the 8 bits. And now I will wait for another 8.7 microsecond for the stop bit. And once the stop bit has been collected, I will transfer this transmitting byte into our actual transmitted data. So suppose the transmitted data is byte transmitted. So that will capture the data of this transmitting byte. Now I have used this another 8.7 microsecond because we would be also getting a stop bit. So we wanted to ignore this. Otherwise, we would be getting some random data for one pulse. Okay, so now this is the time to define these two identifier as a signal. So we have these two signals. So that is transmitting byte. This is std underscore logic underscore vector, and the range will be this. Okay, and we are also having the same signal, and that was transmitted byte. Okay, hope I use the same name. Okay, so let's copy this so that it won't give us syntax error, right? Okay, so let's save this. Now I will go to the model sim, even though let's change the test sequence this time. And this time I wanted to test my module for a large number of test sets. Okay, for example, I wanted to test this module for 255 characters or 255 data. Okay, so one way is that you can use these statements and you can copy them multiple times like this. And every time you can pass some random data. So this is 36, this is 38, 38, something. You can pass any data. So that is one way to do. But what I will do, that I will use another loop here. So for example, I wanted to test my module for 255 times. So what I will say that I will test my module for I in 0 to 255 loop. And these two statements will be passed here. And instead this hard-coded value, I will pass the value of I, and finally AND loop. Okay. So what it will do, that this loop I will run up to 255 times or 256 times even, because that starts from 0. And now this procedure will be called up. So test sequence, and the value will be I. So this test data will be replaced by 0 here in this procedure, and you would be getting 0 as your first test data. Now we will wait for 20 microsecond, and then I will trigger this loop for the another round. Okay, now the value will be 1. So this test sequence will be passed with the data 1, and it will generate the test sequence for that. Your module will receive the data and then it will transmit it back. Okay, and that will happen up to 256 times. Okay, so let's save this program, and now we will go to the model sim simulator. Now if you look at this UART transmitter module for the test bench, so this is question mark because we have changed our logic for this module or this test bench. So we have to recompile it. So right click, compile, and then compile selected. Okay, so there are few errors. So let's see what are these. So it is expecting semicolon at 109, 112, 116, 119. Okay. Okay, so the problem is we didn't use the semicolon here, and also we have not ended the process. Okay, so let's do it. Now save it. Okay, now let's go back to the model sim and let's compile it once more time. Okay, now there are 3 errors. Let's see what are those. Line number 109, 12, and 6. 109. Okay, so we have not used the wait for statement. So we have just waited for some specific time. So we have to use this wait for statement for waiting for some specific time period. So now let's save this and let's simulate our program one more time. So compile selected. And now we have cleared all the syntax error. So now this is the time to restart our simulation. So let's restart it. And now this time I'm not interested in all the signals, but I am only interested in the UART transmitter module signals. So I want this clock, this reset, this transmitter pins, this transmitting byte, or even better to take this byte transmitted. So drag them here in the waveform window. I'm also interested to see the 8-bit received data. So that signal is inside our UUT. So we have this received data as well. So we will drag it. And now we will compare this byte transmitted with this receiver data. If we are transmitting the same byte that we have received at the receiver module or not. Okay. And now because we are transmitting 256 data, so we need to simulate our program for little more time. So for this time, let's say we are running our simulation for 1 millisecond. Okay, so we'll trigger it for 1 millisecond. And now it looks like that we need to test our module for a little more time because we have only received few test sequences, right? So let's run our module for 100 milliseconds. So wait for a while because it can take some time. Okay, so you can see that we have total 101 millisecond of this simulation window. Okay, and I think that's enough time because in the last we are getting all logical high bits. So we will move where the data is changing. Okay, so let's move to the starting point. Okay, so let's change the radix of these two datas to hexadecimal. Okay, so that we can compare the bits and the hexadecimal value as well. Okay, so let's move this transmitted byte in the bottom section so that we can compare it easily. So this is the signal where we are receiving the data and this is the signal we are transmitting the data back. Okay, so you can see that this 00, so that is received here and this data has been passed. Okay, then we have waited for 20 microseconds. Okay, so that is the period because we have written this in the code that after each transmission, where it is, yeah, so here it is. So after each transmission of byte, we will wait for 20 microsecond. So that is the waiting time. Okay, sorry, this is the waiting time here. Okay, you can see that after receiving one complete data, we are waiting for some specific period. Okay, so you can see that after every byte that is received, we are waiting for 20 microsecond. You can calculate this time as well from two markers. And I will do it little later. So first we are just comparing the data. So this data that is received here, so this data has been transmitted back, then this data has been received, this was transmitted back, then this data is received, that is transmitted back, then this. So you can see that everything that is received, that is transmitted back. Okay. So if we go to the last of the changes, so that changes will be near about 255. Okay, so where it is. Now let's change the radix of these two to decimal or unsigned even. So we can see the value of 255 that we have transmitted, or in the hexadecimal that will be double F. Okay, so we can see the last data that we have received is 255 and the same data has been transmitted back here. Okay, so if you wanted to explore that when the transmission has been started, we have already tested this in this session itself, so I think I do not need to repeat it again here. But if you want, you can test it as well. So that's a good thing. And these are our results. So I think this is doing the same thing that we are expecting from our module. So I'm pretty satisfied with the results now. So what I will do next, that I will copy the whole project into the quarters, and then we will see the different type of reports that are generated in the quarters prime. Okay. And that will also tell you about the timing behaviors. And I will also show you that how these behaviors need to be reviewed. Okay. And how to fix if you are capturing any timing violations. And we will also generate a programmer file that can be used to program your FPGA hardware. Alright, so let's move to the Quartus Prime software. So we will open Quartus Prime and we are going to use this version. Okay, so let me move here. So this is our Quartus Prime starting window. So first I will select this new project wizard. Now click on next. Now this is asking that where you wanted to save your project. So let's browse the folder location. Now suppose I wanted to save this inside this Quartus 2 projects. For example, you can select any folder. Now create a new folder and give it some name. For example, the folder name is UART module. That is our project name. Now I will copy this because I can use this later. Now select this folder and now it is asking for the project name. Now remember that your top level module will be your project name and that is mandate. You cannot use two different names for your top level module and this project name. And if you remember that our top level module is UART module here. Okay, so I will use the same name as we have used for designing our top module. Okay, now click on next. So this will be an empty project. So click on this option and then click on next. Now here you can add multiple VHDL files for your project. Like we have used Notepad++ to write our VHDL programs. Then we have used Model Sim Simulator to simulate them. And now we are going to use the same VHDL files in this project. So here I can import all these VHDL files in this project. Okay, so for this I will click on these three dots and I will select the folder location where all the VHDL files are stored. Okay, so what I will do that I will copy those files from the model sim UART project. So that was our UART project. So here we have this source folder, and you can see that all the modules are listed here. So I will copy these and I will go to my folder that is quarters 2 project, and that is our UART module project. So I will paste all these files here. And now I will select all these files and I can click on open. You can also copy this file from the Windows Explorer as well, or even you can directly import these files from your model sim project as well. So all the steps will work fine. Okay. Now what I will do that even though I will create a new folder that is our source folder, and I will move all these VHDL modules in the source folder. Okay. Now I can select all of them and then click on open. So you can see that all the files, all the VHDL files are listed here. Okay. Now click on next. So now this is the page where you can select your FPGA device. Okay. So for example, I'm selecting this Cyclone 4E device. Now you have multiple filters here. So you can select the package. For example, I'm using this QFP package and the suppose pin count is 144. So select this. You have to select what FPGA you have. Okay. And now you can select this speed grade. For example, this is 8 in my case, and you can select whatever FPGA you are using. Okay. So for example, I'm using this for this project. So I will select this FPGA device and then I will click next. Now here you can select your simulator if you wanted to use it. Now because I'm not using it because I have already simulated my project in Model Sim. So I'm not going to select anything from here. So I will leave it as it is and simply I will click on next and then click on finish. So first thing what I will do that I wanted to use the recent compiler for our VHDL project. Okay, so what I will do that I will select this FPGA device that I have selected. Now right click and then click on settings. Now you will see this type of window, and here you need to go this compiler setting and then VHDL input, and you should select this VHDL 2008 version. Okay, now click on apply and then OK. So you can see that we have this module, UART module, as a top level module and as our project. So first thing that I will do that is analysis and synthesis. So you can see that multiple buttons here, so you can use them. So this is the button here for analysis and elaboration. So click on it. So now you can see that process has been started. You can also see the status here at the bottom. Okay, so now this is completed. So this analysis and elaboration that is marked with the green color and that is completed in 8 seconds. Now once you do that, you can see the hierarchy of your top level module. So that is our UART module, which is our top module, and here we have two modules. So that is transmitter module and that is receiver module for UART. Now if you expand them, you can see that all other modules that has been used. So for this RX module, we have used this baud clock generator, we have used shift register and sync component. Same for transmitter module, we have used these two elements. Okay, so that is the hierarchy, and you can select the hierarchy from here. So if this view is not coming for you, so you can select the hierarchy from here, else you can select the files. So all the VHDL files are listed here. Okay. And now because our Quartus Prime software has completed this analysis part, this means that all of our VHDL programs are free from any syntax error. So now what I will do that I will assign the input output pins or input output ports of our top module, and we will map them with the FPGA board pins or FPGA device pins. Okay. And for that we will use pin planner. So if you look at this multiple buttons here, there you will see a pin planner. Okay, so I will open it from here. So you will see this particular view. So this is your FPGA device and that is the device that you have selected. So we have selected this from the Cyclone 4 family, and this FPGA was having 144 pins. So you can see all the pins listed here along the 4 sides of this FPGA. So this is side A, this is B, this is C, and this is D, And our Quartus Prime software also captured all the input output signals or all the input output ports from our top module. So if you look at this table, so we have this clock, reset and receiver as an input pin. Okay. So you can see that Quartus Prime already detected the direction of your input output ports. Okay. So these three are the inputs and this transmitter pin is your output. Okay. So what I have to do, that I have to map the physical pin of this FPGA to these ports of our top module. Okay. So for example, we have this clock signal or clock port, and we can use these pins for this clock signal as an input. Okay. Now the question is that to which pin this clock port has to be connected, and that need to be specified from your datasheet that you will be received from your FPGA board manufacturer. Okay. So if you are using the same board that I have, then you can map these ports to the same pins that I am mapping. But if you are using a board that is manufactured by someone else, then you have to follow that particular datasheet. Okay. So for example, in my case, this pin clock is connected to pin number 23. So what I will do, simply I will write pin underscore then your pin name. For example, I wanted to connect this pin with pin number 23. So once I do this, you can see that this pin 23 is highlighted. And now this is reserved for this clock port. Okay. Similarly, we have this reset input. Okay. So I will write pin number 25, for example. So this particular pin is assigned to the reset of our top module. Okay. Similarly, I will repeat the steps for our receiver pin, that is for UART, and same for UART transmitter pin. Okay. So receiver pin is suppose pin number 115. So that will be pin underscore 115. And suppose this transmitter pin is connected to pin number 114. Okay. Now, if you notice, then when I have updated the location of these ports, our Quartus Prime software already detected the IO banks respected to these FPGA pins. Okay. And this is because these 144 pins of this FPGA must belong to some specific bank. And these banks can be in different numbers for different FPGA devices. So for example, this particular FPGA device have 8 banks, and you can select individual power supply for each individual banks. Okay. So you can take is like this particular FPGA device are divided into 8 blocks like this. Okay. So there are 8 blocks and there are few pins, and each and individual pin of this FPGA must be belongs to one specific bank. Okay. And these are pretty standards for the FPGA devices. So that's why Quartus Prime able to detect input output bank from the pin locations of your FPGA. Okay. And now we have this input output standard. So by default, they are selected as 2.4 volt. Means all of the banks are expected to get the VCC voltage of 2.5 volt for each individual bank. Okay. But if your board manufacturer is using a different power supply or different voltage for different banks, then you have to map it. Okay. So for example, if your FPGA board manufacturer is using 3.3 volt, then you have to select this 3.3 volt. Okay. And maximum manufacturers are using this 3.3 volt standards. So you have to select whatever your board manufacturer is using. Okay. So let's give these settings, and now we have this current strength. Okay. So basically it is telling that how much level of current that pen should flow. Okay. And because we are using a low speed device at the moment, because this is a UART and we are only having the baud rate of 115520, so this is a slow speed device. So for this project, even you can reduce the current strength. Okay. For example, I can use a 4 milliampere. Okay, let's do the same. And now that's complete our pin planning. So these 2 columns are identified by the Quartus Prime, and that is port name and their direction. So we have this FPGA view here. This is our selected FPGA, And here we can see that all the pins are listed here. And then we have assigned the FPGA pin sequence with the top level module or the ports of our top level module. Okay. And accordingly, once we define the location of these ports, input output banks from the FPGA is already defined by the Quartus Prime software. Okay. Same the V reference group. And then we have defined the input output standards as per the FPGA board manufacturers. And we have also defined the current strength based on our project needs, right? So that's complete our pin planner. Now you do not need to save all of these things in Quartus Prime software, because once you change anything here, then these settings are automatically saved. Okay, so you can just close this window. And now what I will do that I will give a full compilation to this top level module. So if you go here, then you will see this start compilation button. Now I will click on it. So it can take little time. So you can see that the progress is ongoing, and same you can see this the status bar here at the bottom section. And here you can see the timings. So now you can see that everything is good, all in the green section. And let me quickly brief what are these things. So analysis and synthesis. So here it will compile your programs or all of your VHDL modules, and then it will convert it into the RTL matrix. Okay, so that's the job of analysis and synthesis. And next is filter or place and route. So whatever the structure that has been generated in the previous step, now Quartus Prime software will place these elements inside the FPGA and also define the route of signals. Means all the interconnections between those elements will be defined by this route. Okay, so that is place and route. Next section is assembler. So here Quartus Prime will generate a programmer file that can be used to program your FPGA device. And the last section is timing analysis. And this section will tell you if your module is violating any timing constraint. Now coming to this main section. So this is our compilation report, and this is actually very important. So first it is showing that what version you are using, what is your top level entity, what FPGA device you are using and belongs to which family. Now total logical elements. So you can see that this FPGA that we have selected, that has 6272 elements inside it. And out of these, we are using 70 elements in this UART project. So this is actually a very small project, okay, which is only consuming only 1% resource of your FPGA, right? Now you can see that you're using 57 registers, and next is total pins. So you know that you are using 4 pins out of these 92 pins available in the FPGA. Okay, so that contributes around 4% only. So these 4 pins are clock, reset, receiving pin and transmitting pin, right? So that's the wholesale summary. But if you look at this tab, you can see that everything is good except this timing analyzer. So you can see that this is in red, means something is not good here. So if you expand this, then you will see there are a few things that are in red. So this is in red, this is in red, this is in red, this is in red. So we need to look at what are the timing problems and how we can solve them. Okay. So if I click any of these red highlighted area, then I can come to know that what is the problem. So for example, for this, I can say this setup summary, and you can see that this clock is having the negative value. These are expected to have a positive value. And because these are negative, so that's why it is in red. Now let me quickly tell you that by default, Quartus Prime software is considering that you are going to use 1 gigahertz of frequency. But for our project, we are expecting to use a 50 megahertz of clock frequency, right? And there is a huge gap. And 1 gigahertz of frequency is really a very high frequency. And if you are using a 1 gigahertz of frequency, then the variation is just 2 nanoseconds. And for this endpoint TNS, that is 76 nanoseconds. So I'm pretty sure that for the 50 megahertz of clock frequency, there will not be any timing problems, right? So we can simply ignore this. But even there is a better way, that I can tell this Quartus Prime software that I'm going to use a 50 megahertz of clock frequency, not 1 gigahertz. Then all of these warnings will be wiped off. Okay, so I will prefer to use that way. But before this, let me quickly brief what all are these things. So you can see that these are started from slow or fast. So what Quartus Prime is doing, that it is considering the fastest model and the slowest model for the FPGA, and then it calculates these values. And it is also telling that how these devices will behave at different temperature. So this 0C means at the 0 degree centigrade and at the highest temperature of 85 degree. Okay. And for this, we can see all of these elements are in red mark. So for this, what I will do, I will tell the Quartus Prime that I'm going to use 50 megahertz of clock frequency. Okay. So first I will click on this button. That is our Quartus Prime timing analyzer. And here you will see this update timing netlist. Okay, so just double click on it so that it can run. And you can see that is in green, so that's done. Now let's minimize this window. So at first I will create a new file. So I will go to this file and I will click on this new. And this time I'm going to create a constraint file. So I have to select this synopsis design constraint file. So this is SDC file. Okay, that is synopsis design constraint file. So that will be present inside this other files. Okay, so I will select this. Now click on OK. And now this is the time to define the clock frequency. So for this, what I will do, that I will go to this edit section, and here you will see the option of this insert constraint. And the first option is create clock. Okay, so I will click on it. And this type of window you will see. Now first I have to give some clock name. So give it, that is 50 gigahertz. You can give any name and it can be different from your top level module port. Okay. Now this is a 50 megahertz and now it is asking for the period. So for this 50 megahertz of clock frequency, the clock period will be 20 nanosecond. So you can see that it is in 20 nanosecond. So for 10 nanosecond that is high, and for another 10 nanosecond that is low. Okay. Now because if you wanted to use a 50% duty cycle of a clock frequency, so you can leave these two fields blank. But if you wanted to change the duty cycle of your clock, then you can tell that when it will have the rising edge and when it will have the falling edge. Okay. Now I have to select the target. So for this I will click on this three dots and it will show up with this type of window. So from here, I will select this get ports and I will click on this list button. So it will list all the ports from your top module. And now I have to map the port which belongs to this clock 50 megahertz. Okay. So this clock signal will be belongs to this 50 megahertz of clock, right? So I will select this and I will move to this selected window. Okay. So this is selected. Now click on OK. So this is the statement that will tell that you are going to use a 50 megahertz of clock frequency and that will be mapped to the clock port of your top module. Okay. Now click on insert. Now click on enter, save this. And now I will save this with some relevant name. For example, this is a timing constraint. So I will save this as the same name so that I can remember what's inside this file. Once you save this, then I will recompile my program. Okay. So I will click in this start compilation button and then it will start everything. So you can see the progress here. So wait for a while so that it can complete. And once it's done, the new report will be generated here. Okay. So you can see that still this timing analyzer is in the red section. Okay. So now I will expand this and now you will see that these elements which was in the red mark, now they are green or they are good. Okay. Means there is no timing violation on the clock signal anymore. Okay. So you can see the setup summary now. So everything is good. There is no red. So everything you can check and even you can go through all of these elements here listed here. But I'm just telling you the important ones so that this video won't be very long. But if you go down and you see, then we still have this red mark section that is inside this unconstrained parts. And if I click on summary, then it is telling that we have two input ports and these are unconstrained. Same, we have one output port that is unconstrained. And that is because these inputs that we are having inside this module, that is our UART module, and all of these three inputs are asynchronous in nature. Means they can reach at the input port of the FPGA at any point of time. And we have synchronized it with the clock internally wherever they are needed, right? So we do not need to worry about the timing constraint of these inputs or even outputs, because output can reach also at any point of time, which we have defined inside our modules, because we have write the VHDL code for them, right? So what we will do, that we will tell the quartus prime that simply ignore these constraints. Okay, so for that, what I will do, that I will go to this timing constraint, and again I will go to this edit tab, and I will select this insert constraints, and now I will select this set false path this time. Okay, so once I will select this, I will see this window, and that is showing from and to. Now because let's define them for the inputs, so I will select this from tab. Okay, so for this I will click on this three dots. Now I will select the ports from here, and then I will click on list. Now it is giving me error that timing net list does not exist, because that is updated and we have not selected it again. So for this, what I will do, that I will cancel everything and I will open the timing constraints once more time. So this is our timing analyzer, but remember I have not closed this window. So this is already opened in the side here. So if you see that this is not ready at the moment, because these are marked as black color. So what I will do, I will simply double click here, and you can see now this is done. Now I will minimize this window and follow the same steps again. Okay, so go to edit, now insert constraint. Now click on this set false path. Now click on from, because we are now doing this for the input ports. So we will click on these three dots. Now select the ports. So get ports. Now list them. So now you can see that everything is listed here. So we have 4 ports, and from these 4 ports we have 2 as an input, because for clock we have already defined the constraint. Okay, so we have this receiver pin as an input and this reset pin as an input. So I will move them to the selected area, and now click on OK, and now select this insert. Okay, so these are inserted. Now save this, and now we will repeat the same step for the output port. Okay, so again I will go to this edit tab. Now click on this insert constraint. Now select this false path. Now because this is an output, so I will select 2 this time. Okay, now click here on these 3 dots. Now select the ports, so it will get the ports. Now click on list. Now this time this is coming because I have not compiled my program yet. Okay, I will do it single time after doing this. Okay, now I have to select the output port, and we have this output port. Okay, this is the only output we have. So I will select this and I will move to this selected area. Now click on OK, and now click on insert. So these 3 lines are inserted, one for the clock signal or clock input, these two for the 2 input ports, and the last one is for the output. Okay, now save this, and now we will compile our program one more time. Okay, so click on this button. Now the compilation is started, and you can see the progress here. So it can take little time. So we will wait for it to complete, and you can see that's about to complete, and that's completed 100%. Okay, now if you focus here, then there is no violation about timing. So now this is not in red. Okay, so that's good. So what we have did, we have compiled our program for any syntax error, and we have developed the synthesis from here. Then we have given the pin planning, where we have specified all the ports and mapped that with the FPGA pins. And then accordingly, Quartus have generated the place and route files and performed this action. And once it's done, it has generated the programmer files for us. And we can also see multiple files for different type of reports that you can analyze based on your needs. Okay, and I have showed you whatever is in red, and I've also told you that how to fix them. Okay, Now, if you wanted to implement this program into the FPGA board, then simply you need to open Programmer. So if you move to this buttons here, you will see the Programmer. Okay, so simply open this, and this is your Programmer module or Programmer window. So let's quickly see what it is here. So this is your top level module. So that is your UART module.sof. So that SOF is your programmer file that you can use to program your FPGA device. Okay, this is the device name that you have selected. This is the checksum, kind of a verification done by the Quartus Prime software. This is a user code, you can ignore this. And we have this program or configure button, so that is ticked. Okay. Now this time I have not connected with any hardware or any FPGA device. So that is why it is showing me no hardware. But if you connect your FPGA device with the J tag, then your device will be listed here. Okay. If not, then you can click on this hardware setup, and that hardware must be listed here in this box. Okay. You can just simply select it and then click on close. And once you do this, and once you select this programmer file, you will see that this start button will be highlighted. So once it's highlighted, you just simply click on this start button, and then you will see the progress here. And once it's 100% complete, then your top level module will be implemented into your FPGA device. Okay. So that's how you can program your FPGA device and load this SOF programming file into the FPGA device. Okay. Now let me quickly show you the folder that has been generated by this Quartus Prime software. Okay. So I will open the file explorer, and here you can see that we have developed our program for this UART module inside this Quartus 2 projects folder. And here we can see this UART module. So that UART module is our Quartus project. So that is QPF in format. And we have this source folder that we have generated or that we have created to copy all our VHDL modules or all of our VHDL files. So you can see that all the VHDL files are listed here. And if you see, then there is one more folder that is generated by Quartus Prime. Okay. If you open it, then you can see there are multiple files are generated. So I have already told you about this SO file. So that is your programmer file, and you can use this file to program your FPGA device. And you can see a couple of more files here that you can do it in the notepad. But the one file that I wanted to show you, that is QSF file. Okay. So that is your Quartus setting file. And whatever the settings you have used in your project, that all the settings are listed here. So if you open this into the notepad, so open with in the notepad, then you will see all the settings are listed here. Okay. For example, what device family you have selected, what FPGA device you have selected, what is your top level entity, what Quartus software version you are using, date and time when it is created. Also, all the VHDL modules are listed here that you have used. So you can read this one by one. But important thing is this pin section. So you can see that whatever the pins we have defined for our top module, so these are also listed here. So you can use them and you can change them as per your need as well. Also, you can see that we have changed the voltage level or the input output standards from default to 3.3 volt. Okay. So you can see that we have changed this for all these 4 ports. Okay. Same, we have changed the current strength to 4 milliampere so that you can see. So whatever the changes except the default things you have made into your Quartus Prime software. So all of these settings are recorded here. Okay. So you can use this file as a reference. Okay. So that's it for today. That was our complete UART project where we have designed a UART transmitter. We have designed a UART receiver, and then we have designed a UART module that was echoing back the received data, and the data that has been received at the receiving port that has been transmitted back through the transmitter module. Okay. So I think that is a good practice project, and hopefully you have learned something from this complete project of this UART module.